weeks. So try to block out the rest of the world for 2 weeks here as much as hard as you can. And after we get through finals, then you can really have a better break over Christmas and winter. Okay, so do Friday are a couple of ANOVA problems. Notice on the first one, I peeked in the solution manual and it wasn't terribly clear. On 11.4.5, when you actually do that, you actually reject the null hypothesis on that first problem when you go through and you do it. Now, normally what you would do is you would do all of the Bonferroni pairwise comparisons to see where the differences lie between the 5 groups. But with 5 groups, that's 10 Bonferroni pairwise comparisons, and that's probably not a path we really want to go down. So just do the overall ANOVA test, but don't do pairwise comparisons on that first problem. On the second problem, you also reject the null hypothesis. There's only 3 groups, so there's only 3 pairwise comparisons you have to do. 1 versus 2, 1 versus 3, and 2 versus 3. Okay. So keep that in mind. Normally, what you would do is, if you didn't reject the null hypothesis, there would be no need to do pairwise comparisons. You just stop there. But on number 1, since we reject, normally you would do them on the first problem. But let's skip that. Okay, and our final is Friday of finals week. The plan for the final, you guys, we have 2 hours on the final. Instead of doing 20 questions, we'll do 25 questions on the final. So time-wise, it's going to be a lot more laid back than the midterms, which will be nice. The final will be cumulative, so it'll be about 40% kind of old stuff and about 60% kind of new stuff after the 3rd midterm. So if you still have your first exam sheets, reuse those, and like late this week or next week, I'll give you guys an extra exam sheet for the final. So for the final, it's going to be quadruple cheat sheet. Like, holy cow, yeah, that's pretty good. Okay, good. Okay, so you got any questions or anything before we get rolling? Are you guys feeling super happy to be back? Yeah, not terribly. That's okay. Yeah, okay. Just give it your all for the next 2 weeks here, and we can all kind of take a break. If you remember where we left off, we were looking at a little problem here, which we'll be working on for a while. We have 4 students, and for each student, I recorded 2 pieces of information: how many hours that they study for an exam, and their subsequent exam score. Okay, and we kind of made a scatter plot of the 4 students, and you will notice that the points are going in an upward pattern, which is indicating that there's a positive correlation between hours studied and exam score. The points don't fall directly on a straight line, so the correlation isn't +1, but it's pretty close to it. I think the correlation is going to be pretty close to +1. If I looked at that, I might say it's like 0.9 or 0.95 or something. I think would be a good guess. Let's actually compute the correlation. Yeah. So part A, or part B, I guess. Let's compute R. So let's compute Pearson's sample correlation coefficient, little r. And so here's my data here. So the correlation, let me just write it down. It's the sample covariance between x and y over the standard deviation of the x values times the standard deviation of the y values. Okay. So this is how you find a correlation. So let's kind of walk through and see how to figure this guy out. First of all, what's my sample size n? Like, how many people do I have in my study? 4, so n is 4. Now, x bar is simply the mean of those 4 x values. So it's just 1 over n times the sum as I goes from 1 to n of xi And so if you take the average of those 4 x values, what you get is 9. Okay. Y bar is just the mean of the y values. So it's 1 over n times the sum as I goes from 1 to n. I guess we could do yi. Okay. So if you add up those 4 y values and you divide by 4, what that poops out is 74. Okay. So for the 4 students in my sample, the average score was 74, and the average time spent studying was 9 hours. And, okay, so how about this? S sub x is the standard deviation of the x values. So if you recall, this is going back to like week 1. It's 1 over n minus 1 times the sum as I goes from 1 to n of xi minus x bar. What do you do to that difference? You take that difference and you square it. Okay? You guys remember doing that a long time ago? Okay. And so it's just the standard deviation of the x values. And so if you do that, I guess you get 1 over 4 minus 1 times. And what this is saying is when I is 1, you get x1 minus x bar, so it's going to be 10, minus x bar, which is 9. You take that difference and you square it. And you go down the whole line up to x4 minus x bar, which is also, I guess, 10 minus 9 squared. And what you get when you do this guy is 5.03. That's just the regular sample standard deviation of the x values, okay? No problem. Okay. S sub y is just the standard deviation of the y values. So S sub y, if you wrote it formally, is the square root of 1 over n minus 1 times the sum as I goes from 1 to n of yi minus y bar squared. Just the standard deviation of the y values. And I won't bore you with the computation. If you find S sub y, the standard deviation, that gives you 18.76. Okay. All right. Okay, now, the last piece we need up here is the sample covariance. So let's find it. So the sample covariance. Sounds like the room is like today. It's very loud. The sample covariance is 1 over n minus 1 times the sum as I goes from 1 to n of xi minus x bar. But do you guys remember, do I square that difference? I don't. I multiply it by yi minus y bar. Okay. The room's like burping and farting. That's much sure why. Okay. So what do we get? So you get 1 over 4 minus 1 times. Now, what we have is you take, when I is 1, you get x1 minus x bar. x1 is 10 minus x bar, which is 9, times y1 minus y bar. y1 is 82 minus y bar, which is 74. Does that make sense? Okay. Plus, and you keep going. Then you take x2, which is 14, minus x bar, which is 9, times 94 minus 74, plus 2 minus 9 times 50 minus 74, and finally 10 minus 9 times 70 minus 74. Is that okay, guys? Okay. It's not hard, but it's kind of a pain in the rump, okay, to get it. But if you punch this in, now remember, the covariance tells you if there's a positive association or a negative association. I think when I compute my covariance, that's going to be positive because we have a positive association. And when you compute your covariance, that gives you 90.67. So that is indicating there's a positive association between our study and exam score. i.e. the more that you study for the exam seems to increase your exam score in some sense. Okay. Now, is that covariance strong or not strong? Looking at the covariance in and of itself, it's hard to tell the strength of that relationship. But what the correlation does is, the correlation kind of scales your covariance and makes it fall between -1 and +1. So take your covariance, which is 90.67, over the standard deviation of the x values, which is 5.03, times the standard deviation of the y values, which is 18.76. Okay. Now, after a little prayer, our correlation has to fall between what and what? Between -1 and +1. Okay. If we don't fall between -1 and +1, what do I know for sure? Something's off the rails somewhere. Okay. If you compute that guy, what you get is you get 0.961. Is there a pretty strong linear relationship between our study and the exam score? Totally, yeah. Okay. And so looking at the covariance in and of itself, that's hard to say, but the correlation scales your covariance between -1 and +1, allowing you to make an assessment of the strength of that association. So there seems to be a pretty strong association there. Okay. All right. On the homework, you guys will do for next week. You'll do one correlation. You'll compute from by hand. What's the probability I would ask this on the final exam? Probably pretty slim, right? Including me, what's the probability on an exam we would punch everything in and get the right answer? It's probably pretty slim. It's good to do the correlation once by hand, but after that, just use a computer. It's not hard, but it's very tedious and pretty error prone. So, okay. All right. So let me show you how to do this on a computer. And just really quick, I mentioned R before. If you put R on your computer, this is what it looks like on a Windows computer. If you put R on a Mac, you would just run it within a terminal. It's a little bit nicer on a Mac. So let me show you how easy it is to compute the correlation. So I have a bunch of x values. So what I'm going to do is I'm going to do x, the less than sign, and a minus. Now when I do a less than sign and a minus, it kind of looks like a left arrow, kind of, okay? And inside of x, I'm going to store the following. I'm going to do C. It's going to be 10, 14, 2, 10. Okay. And when I hit enter, what it's doing is it's storing those data values, 10, 14, 2, and 10, the hours studied, in that variable called x. Okay. Now for y, let's put in the exam scores. So the same thing. We'll do y. We'll store the exam scores, which is 82, 84, 50, 70. I have the y scores. I have the exam scores stored in y. And you can actually see x and y really easy. If I just type x, it shows you, hey, those are the hours studied. Y is the exam scores. Okay. Now, if you want to plot, if you want to make a scatter plot between those babies, watch this. So if I just do plot x comma y, oh baby, okay, and if you look at that graph, hey, it did a scatter plot just like what we did by hand, okay? And that graph is pretty sexy looking, and you think that's good enough for like a publication? Yeah, totally, yeah, these are total publication quality graphics you can get out of R really easy, okay? So, you think R can compute the correlation for us? Yeah, I think I can do a sample covariance between x and y. Yeah, 90.67. Isn't that beautiful? It gets it for you really easy. And if you want the correlation between x and y, 0.9961 or whatever. So it's super easy to get the correlation and covariance and everything just directly out of R. And it's good to do it once by hand to torture yourself. But after that, you just use some. Okay. Okay. So let's note the following. If two variables are correlated, one does not necessarily cause the other. What people kind of say in real life is correlation does not imply causation. It's kind of what you see. Now, this is a really important point. What am I getting at by this? What if you look at ice cream sales versus drownings? And if you had two variables, ice cream sales and drownings, I guarantee there is a positive correlation between the rate at which ice cream is being sold and the number of drownings that we see as a community. Okay? In other words, when ice cream is selling really, really well, quite a few people are drowning, relatively speaking. And when ice cream is selling really, really poorly, very few people are drowning. Sure, okay? Does it mean ice cream is causing you to drown? Does it? Yeah, I ate ice cream before swimming many times. I never sank to the bottom, you know? And so, yeah, there's a positive correlation there, but it doesn't mean ice cream is causing you to drown. Is there an explanation for why there's a correlation there? Yeah, totally. What's the explanation? It's like kind of summertime maybe, you know what I'm saying? Yeah, in summertime, everybody's out swimming because it's nice and everybody's eating ice cream, you know? Wintertime, most people don't eat ice cream except for me, and not many people are swimming, you know, so there's very little drownings. And so just because they are correlated doesn't mean one is causing the other, okay? Yeah, so, and if you watch for this in the news, this pops up in the news quite often where they get really excited. You know, there's an association between these two variables. And most of the time I say, well, so what? I mean, you know, it doesn't mean one's causing the other at all. Okay? Yeah, and one that was in the news is, you know, certain neighborhoods, you know, have a much higher rate of heart attack than other neighborhoods. Okay? Well, so what? I mean, if you move to a neighborhood, does it mean you're going to die of a heart attack? No, I mean, there's other factors that are at play here in the neighborhood. Not the neighborhood itself is killing you. It's you know, it's just kind of the culture of the people there, I guess, you know. So, yeah, so just really watch for that. Okay? So I guess so far, we're able to kind of say, hey, it seems like there's a positive correlation between our study and exam score. We would like to maybe look at this a little bit more in detail, and the correlation kind of gives you an overview of the relationship. Let's get into a little more detail using a method called simple regression. So, simple regression. And the name simple regression, it's a little bit unfortunate. It's not simple, I think, but it's kind of the simplest scenario that you can have in a regression setting, which is why they call it simple regression. But it's kind of a stupid name, I think. So, okay, little note. We want to investigate how changes in one variable many times just known as your explanatory variable. The corresponding to changes in another variable. Known as your response variable. And so we want to investigate how changes in one variable correspond to changes in another variable. Okay? And the technique that we're going to use to try and explain it like this is known as simple regression. Okay? So simple regression is going to allow us to kind of describe our data in this particular context. Now, just kind of bear with us for a little bit. We use the least squares regression line. Now, the so-called least squares regression line, I'm going to write as follows. It's y hat is equal to beta 0 hat plus beta 1 hat times x. Okay. So we want to use this least squares regression line, which takes this form, to infer about the population regression. And the population regression line is going to take the form, it's going to be mu sub y given x is equal to beta 0 plus beta 1 times x. So let's just step back and kind of think of what we have in terms of our study exam score. Okay. So we're going to use what's known as the least squares regression line, which is y hat is equal to beta 0 hat plus beta 1 hat times x, to infer about the so-called population regression line, which is mu sub y given x, it's beta 0 plus beta 1 times x. Okay. Now, just from a pure algebraic point of view, you guys know what a line is, right? Whenever you have a line is defined by, number one, its intercept, and number two, its slope. Okay? And so in my notation, beta 0 hat is my intercept, and beta 1 hat is my slope. It describes the slope of the line. Okay? Same with my population regression line. Okay? Now, kind of the big picture is this. Hundreds and hundreds of people took the exam. Okay? And if you envision getting data on every single person that took the exam, if I put them all on my scatter plot, I would have a scatter plot with hundreds of points in it. And if I drew, in some sense, a line through that big cloud of points, that would be my so-called population regression line. Okay? Now, the point is, though, do I have data on the hundreds and hundreds of people that took the exam? I don't. Okay? So from that large population, we got a sample of size 4. Okay? And for the people in my sample of size 4, we're going to fit a line through those 4 points in my scatter plot. Okay? And we're going to use the line fitted to the data that I collected in my sample. And I think the line that I fit to the 4 randomly selected people in my sample should be not unlike the line I would get if I had data on everybody. Now, would you guys buy that? Okay. If I collected data on everybody, I would have a scatter plot with hundreds of points in it. Imagine drawing a line through the center of that huge cloud of data. Okay. If I select 4 people at random, the line that goes through those 4 people should be relatively close to the population regression line. Would you guys kind of buy that? Okay. This is kind of akin to, we didn't know the population mean mu, and what was my best guess at mu? My sample mean x bar. Okay, it's a very similar kind of scenario. Okay. So this is kind of where we're headed. So what is mu sub y given x? Mu sub y given x, in our current scenario, it's the population mean exam score for students that study X hours. So what mu sub y given x is, in real terms is, it's the population mean exam score for students that studied X hours. Okay. What is my best guess at mu sub y given x? My least squares regression line is going to be my best guess in some sense. Okay. Okay. So let me ask you this. Okay. Here's our data set. Now, hundreds of people took the exam. Okay. Imagine me getting data on everybody, plotting them in this scatter plot. I would have hundreds of points in my scatter plot. Okay? Just envision that for a second. Here's the question I have for you. If you had to guess at the mean exam score for people that studied 5 hours, what would you guys say? Take a guess at the mean exam score for people that studied 5 hours. Just kind of look at the graph and kind of tell me what you guys would say. In the ballpark of what would you say? 60-ish, maybe? Would you guys agree with that? Maybe I think a ballpark of 60, maybe. Okay. Would you guys kind of agree with that? What you guys just did in your head was simple regression. I think what you did in your head was you drew a line through the center of this data set, and you asked yourself, how high is that line at 5? And the height of that line at 5 would be around 60. Would you guys agree? That is simple regression. Okay? So what we're going to do is we're going to figure out a mathematical way by which I can draw a line through the center of my data set. And we're going to use that line to answer questions like approximate the mean exam score for people that studied 5 hours. Okay? That's really where we're headed. Okay. So how do we do this, guy? So continue our example. I don't know what part this is. Let's find the least squares regression. Okay. So the least squares regression line is y hat is beta 0 hat plus beta 1 hat times x. And just to refresh your memory, n is 4, x bar was 9, y bar was 74, the standard deviation of the x values was 5.03, standard deviation of the y values was 18.76, and the correlation we found is 0.961. Okay? Those were our summary statistics that we found earlier. So, okay, so the question is, well, how do you find the intercept beta 0 hat and the slope beta 1 hat? Now, I can't get into where these come from, but for those of you guys that have taken calculus, when you're trying to minimize something, what do? You're going to take a what? A derivative. Okay. You're actually taking two partial derivatives. You're setting both to 0 and solve. Okay. Now, what you get when you do that is when you find the intercept and the slope, be sure you find the slope first. So, and the way you find the slope is you take your correlation coefficient times s sub y over s sub x. And if you do a little bit of calculus and solve, you can show that the slope turns out to be this quantity here, okay? Through the miracle of calculus. Okay? So, can I find the slope with what we found earlier? Yeah, totally, right? So let's find the slope. So you take the correlation, which is 0.961, times the standard deviation of the y values, which is 18.76, over the standard deviation of the x values, which is 5.03. And the slope of my least squares regression line turns out to be 3.58. Beautiful. That's the slope. Okay. Now, if you think of my scatter plot, are we surprised that we have a positive slope going through the center of the data set? Not surprising at all. Now, after you have the slope, now you can find the intercept. And the way you find the intercept, beta 0 hat, is you take y bar minus beta 1 hat times x bar. Again, this is from calculus. Okay. Well, can I find the intercept? Yeah, no problem, right? And why do I tell you to find the slope first? Because you need the slope to find the intercept, okay? So, but we have everything now. So it's gonna be 74 minus beta 1 hat, which is 3.58, times x bar, which is 9. And this guy poops out 41.78. Beautiful. Okay. So let's plug that into my least squares regression equation. So you have beta 0 hat, which is 41.78, plus beta 1 hat, 3.58 times x. That's my least squares regression line. Okay. All right. Now let's graph our line. Do you guys remember how to graph a line? Probably not. That's okay. If I told you where I had 2 points, if I had 2 points on the line, could you then just draw the line in? Of course. So what I'll do is let's figure out 2 points on the line. Okay. What I'm first going to do is let's figure out how high the line is when x is 0. So when x is 0, let's plug into my least squares regression line. Y hat is 41.78 plus 3.58 times x, which I'm assuming is 0 right here, which gives you 41.78. What we just did here was, when x is 0, the height of my regression line is 41.78. Let's graph that in. So here's 0 for x. The height of the regression line is 41.78, right about there. Okay. So there is 1 point on my line. Now, if you want to make an accurate line, would I choose x equals 1, or would I choose an x value further out? Yeah, let's choose an x value further out to make a nice graph here. The other x value that I chose was x is 10. Okay. When x is 10, what's the height of my regression line? Y hat is 41.78 plus 3.58 times 10, which poops out 77.58. So when x is 10, the height of my regression line is 77.58. Let's graph that in. 10, 77.58. I'm about here, like so. Okay. I now have 2 points on my line. Let's connect the dots and see what we get. Okay. I'll try to make this look like I'm as accurate as possible here. Yeah, it's not too bad. Okay. That's my least squares regression. Okay. Okay, now, same question as before. Approximate the mean exam score for people that study 5 hours. What would you say? Approximately how high is that regression line around 5? It's approximately around 60, like you guys said earlier. Okay? So what you did in your head was actually, I think, doing what I just did here kind of mathematically. Okay, now, what do we use this guy for? Okay. So part C, I think. Let's approximate. Mu sub y given x equals 5. Now, what is that quantity? What am I asking for? I want you to approximate the population mean exam score for students that studied how many hours? 5 hours. So what I'm approximating here is this. Hundreds of students took the exam. Okay? A subset of those guys studied for 5 hours. If I collected all the people that studied for 5 hours and I averaged their exam score, approximately what would I get? That's the question. Okay? And for me to approximate mu sub y given x equals 5, all I'm going to do is I'm going to plug in 5 into my least squares regression equation. Okay? That's all you do. And so I'm going to take my least squares regression equation, which is 41.78 plus 3.58 times 5 for x. And what this gives you is 59.68. So what is my best guess at the average exam score for students that studied for 5 hours? About 59.68. Okay. Graphically, what we just found was 59.68 is the height of my regression line at 5. Okay. So 59.68 is the height of my regression line at 5. That's all it is. Isn't that cute, right? Okay, how about this? D. Let's approximate u sub y given x is 15. Okay. You guys tell me what I'm asking here is. I want you to approximate the population mean exam score for students that studied 15 hours. Okay? Can you approximate that guy? No problem. So you just plug into your least squares regression equation. Times 15. That gives you 95.40. Okay, good. And so what we just found was the height of my least squares regression line at 15 is right at 95.40. Perfect. Okay. So everything's beautiful. Life is good. Let me ask you this. Let's approximate u sub y given x equals 8. Total hardcore student here. Okay. They studied 80 hours for the exam. Okay. And so if I collected all of the students that studied 80 hours for the exam, what would be their mean exam score? No problem. So let's do the same thing. Take y hat is 41.78 plus 3.58 times 80. And what this gives you is 328.18. The high exam score is 100%. The wheels just fell off our little party here. And can you guys kind of see what may have happened? Let me show you the graph again. Notice that originally we approximated the mean exam score for students that studied 5 hours, no problem. Okay. Then we approximated the mean exam score for people that studied 15 hours. That was no problem. Okay. But where is 80? 80 is way the heck out on the right side over here. Okay. And my point is this: if you're going to do regression, you can make these. You can make these estimates by plugging into your least squares regression equation for x values within the range of your original data, or maybe just a hair outside of the range of your original data. My biggest data point's 14. Could I make a decent prediction at 15? That's okay. But when you try to make a prediction way outside of the range of your original data, can you run into problems? And the answer is yeah. And this is known as extrapolation. And so making a prediction way outside of the range of your original data is known as extrapolation. And when you do extrapolation, can you very easily run into trouble? Very easily. Okay? You know, I mean, in the news, there's a lot about global warming. Okay? If these guys want to make, you know, a prediction like 10 or 20 years into the future, I'm totally on board. No problem. Okay? But if they're making a prediction way into the future of like 200 years, have you pretty much lost me? Yeah. Not only are their estimates probably going to be wrong, they're probably going to be wrong big time. Okay. So again, there's really no free lunch here. I mean, you can make predictions within the range of your original data, just outside. But once you start making these, when you start doing extrapolation, all bets are off. You're going to get into trouble. All right. How about this? F. Let's approximate. U sub y given x is equal to 0. In words, what are we finding? It's the mean exam score for students that studied? Not at all. It is part. Okay. And so what do we get? It's 41.78 plus 3.58 times 0, which gives us actually 41.78. Which, remember, that's my intercept, beta 0 hat. Okay. So in this particular example, does the intercept kind of have a nice meaning for us? Yeah, it does, right? The intercept, it's my guess at the mean exam score for students that study 0 hours. Okay, it has a very nice interpretation. Okay, G. Let's approximate the mean increase in exam score for each extra hour study. Can you guys kind of tell, if you look at my least squares regression equation, what am I kind of asking about? What's the one term that's going to kind of help me answer this question? For each extra hour that you study, how much extra boost are you getting in your mean exam score? Okay. Now, if you look at this, equation, what if you studied for 10 hours? For people that study 10 hours, the mean exam score is 41.78 plus 3.58 times 10. Okay. For people that studied 11 hours, it's 41.78 plus 3.58 times 11. Which group has a higher mean exam score? The 10-hour people or the 11-hour people? The 11-hour people. By how much? 3.58. Okay. So your slope, remember, the slope of a line, it's rise over run. Okay. So for each extra hour that you study, how much do I have to pop up to remain on the line? I have to pop up by 3.58. So for each extra hour that you study, your exam score goes up by 3.58 on average. And so to answer this question, this is nice because that is just my slope. So if I had a group of 10-hour students and I had a group of 11-hour students, which group is gonna have a higher mean exam score? The 11-hour. By how much approximately? 3.5. Okay. Isn't that beautiful? Okay. And so we're able to make these very nice inferences using that least squares regression. Okay. So let's do this very quickly. If we collected data on another 4 students, my intercept beta 0 hat and my slope beta 1 hat would change. Would you guys buy that? If I just randomly selected another 4 students, my scatter plot's going to change a little bit, and the resulting best fitting line is also going to change a little bit as well. Okay, the intercept and the slope are going to change a little bit. Okay? Now, one question you might have is, from sample to sample, how much does the intercept and slope, how much do those guys change? Okay? And those are described by what are known as the standard errors. And so the estimated standard error of beta 1 hat, this describes how much beta 1 hat changes from sample to sample. Okay. So the estimated standard error of beta 1 hat describes how much those beta hats change from sample to sample. Okay. And the estimated standard error of beta 0 hat, that describes how much the beta 0 hats change from sample to sample. Okay. Now, there's actual formulas out there to compute this, but what I want you guys to focus on is the following. If the estimated standard error of beta 1 hat is large, what that says is, every time I get a sample of 4 students, and I find the least squares regression line, the slope of those least squares regression lines are going to be really erratic if the estimated standard error of beta 1 hat is large. Okay? If the estimated standard error of beta 1 hat is small, what does that say? From sample to sample, do those slopes change very much from sample to sample? Very little. Okay? So that estimated standard error of beta 1 hat is describing how much will those slopes change from sample to sample. For us, do you think the estimated standard error of beta 1 hat's on the big side or small side? I only have 4 people in my sample, right? With only 4 people in my sample, do you think the slopes would change quite a bit from sample to sample? I think so. I agree. Okay. If I had 40 people in my sample, do you think the slopes would be a lot more consistent from sample to sample? They would be. And my estimated standard error in that case would be on the small side. Okay. And very similarly, the estimated standard error beta 0 hat, what is that describing? It's describing how much the intercepts change from sample to sample. Okay. Yeah. Okay. I'm not going to show you guys how to compute it. It's not exciting, but as long as you kind of know what it means. Okay. Thank you guys.